Okay, so we're now into our second entropy lesson, and this first slide is really going to set up the next lesson of where we're going. Gibbs free energy is sort of going to come out of the second law of dynamics. Okay? We're going to end up breaking this into two pieces and being able to solve for the two pieces right away. Okay? So we're going to turn that bullet into an equation. During a spontaneous process, the entropy of the universe, the system, and the surroundings must increase or at least stay constant if something is in equilibrium. So if something is spontaneous.
Good morning, everyone. Sorry for the interruption. If I can have all grade 11 classes with teachers down.
Okay. So the change in entropy of the universe must be greater than 0. Okay, that was a big theme of the minute physics videos. Or we want to sort of break this apart, break the universe apart. So the change in entropy of the universe, we're going to look at the change in entropy of the system. That's what we've always been looking at in enthalpy. We looked at change in entropy of the system, but the universe is the system plus the surroundings. So SURR is surroundings. So those two pieces must be greater than 0. And in the following slides, we'll look at calculating the entropy of the system, and then we'll look at how we can get the entropy change of the surroundings. Now, if we were at equilibrium, the change in entropy of the universe, which would be the sum of those two pieces, the system and the surroundings, they're going to sum to 0. Now I'm writing out all of my subscripts, but typically the system is dropped. So you're working through a problem, or I'm writing stuff on the board and I don't put in a subscript, it is the system. Okay, so we're going to predict the entropy change of the system first. This is where advanced placement is often not any more difficult or sometimes easier than regular 30. We're just building off skills. So the change in entropy of the system you can get from a sum. We're going to do exactly what we did to predict enthalpy changes back in Chem 30. If you take the sum of the moles times the standard enthalpy of the products minus the mole times the standard enthalpy of the reactants, you can predict the standard enthalpy of the system. Now I wrote in system. I'm just going to take this out to start getting you used to having that subscript not being there. That's the system. And we'll do this for the open combustion of ethane. If you're on an exam, you'd be given a data table, or whatever textbook you're using for homework will have data tables that you need to flip back to find these. Unlike Chem 30, where you had a the big Chem 30 data table that was separate from your textbook. So a little bit of organic chem review. You should know what ethane is. You're very comfortable with open complete combustion. So F is 2, ane 2N plus 2, so double the carbons plus 2, so that is 6. Ethane is a gas. When you balance this using whole numbers, And we're predicting the standard change in entropy. Now, before I do the math, we're going to make a bit of a prediction. I might ask you to make a prediction. Okay? Do you think, or what is the entropy going to do? Is it going to increase or decrease, or kind of hard to tell? Okay? So we're going to look at our states. We've got a whole bunch of gas and a whole bunch of gas. So we don't have any big state changes. So we can't use solid to liquid to gas to make our predictions by itself. But if we dig a little deeper, we've got 2 and 7. We've got 9 units of gas at the beginning, and that's going to turn into 10 units of gas. There's more gas phase units at the end than there are gas phase units at the beginning. Okay? So we'd expect a slight increase in entropy with that little bit more gas. It's 10 to 15% more gas at the end than there is at the start. 1 unit divided by 9. Okay? But ultimately, we want to do the mathematical prediction, but we're expecting a positive number. So we start with products. We have 4 CO2 times, you go to a data sheet, you look up carbon dioxide, and make sure you don't go to the wrong data table. You now might have entropy, enthalpy, and Gibbs in data sheets. So just make sure you go to the right page, the right data sheet. So 213.6 joules per Kelvin. Okay. Now in AP, they had add in this per mole that we didn't sort of use in Chem 30. So that's CO2 plus 6, water, and this is water vapor. Now my brain is so used to going kilojoules per something, but it's joules per Kelvin per mole. That's my 2 products. Go on to my reactants. And last, I have oxygen. Now in enthalpy, the formation of anything in its elemental form was 0, but that's not true in entropy. You still have to look up your elements. So our oxygen is 205.0 joules per Kelvin per mole. Okay? There's not 0 entropy for elements. Okay? That is not the case. Okay. So you throw this in your calculator, you get your answer. I'm not going to, this is so similar to before. It's something that you'll do with great success. And I get 92.6 joules per Kelvin. And this isn't per gram. It is all being done per mole of reactant. Okay. And we did get a positive value that we would expect with the 9 moles of gas turning into the 10 moles of gas. Okay, so I'm just going to take my answer that I have at the bottom, and this is for the equation. There is a positive, so an increase of entropy of 92.6 joules per Kelvin. Now I've kind of run out of room. Okay, and in Chem 30, this is how we would have written it, but in AP, they put in per mole. Those Kelvin moles are together, meaning that this isn't, you know, the stoichiometric number. This is when we use molar amounts. Okay, so this isn't a molar entropy. Okay, it's just when 2 moles and 7 moles makes 4 moles and 6 moles. This balanced equation gives this standard entropy change. They're locked together. Okay, our brains are used to, from Alberta Chem 30, with the mole thinking molar, but it's not. Okay. So we're mostly done. We broke the change in entropy of the universe into system and surroundings. System is just like before, and now we're going to tackle the change in entropy of the surroundings. So I'm going to put up a little visual I've used before. We have our system. I want to stick that in a cloud. We've got our surroundings. I'm just using SURR. And now we want to talk about the entropy change in the surroundings. So there's no chemical reaction there. That's like the water in a calorimetry experiment that's just surrounding our experiment. The only thing going on in the surroundings is really whatever heat is pushed to it or taken from it. The only thing driving the entropy change is whether it's warming up or cooling down. So that's where the basis of the equation for the change in entropy of the surroundings comes from. So we're talking about the change in entropy. It'll be standard of the surroundings. I'm using SURR. Okay. We're not using products minus reactants here. Okay. What is causing the entropy change here? It is ultimately being driven by the Q, the heat that's going into or out of it. Okay. Again, there's no chemicals reacting in the surroundings. That's all in the system. There's just not a lot going on in the surroundings, okay? And entropy is scaled per temperature, per Kelvin, okay? Okay. Now we're going to write the Q, the joules per mole in Q, okay? We're going to go a little further, okay? Particularly under standard, or under constant pressure, we have QP. And what was QP equal to 2 lessons ago? That was the definition of enthalpy change. Okay? The Q under constant pressure is enthalpy change of the system. Okay? It's not the enthalpy change of the surroundings, it's enthalpy change of the system. Okay? We've got that divided by temperature. We almost have our relationship. We're missing sort of one piece. We kind of have the wrong perspective. Okay. Okay. If when heat, or if heat Q is pushed to our surroundings, okay, what's the entropy going to do? Is it going to increase or decrease when heat is pushed to the surroundings? Okay. When something gets hotter, the entropy goes up. That's sort of back from our first slide of the previous lesson. When things get hotter, there's a bigger distribution, the entropy is increasing. Okay? So when heat's pushed to this, we need to get a positive entropy. Okay? When heat is pushed to this, enthalpy change of the system would be negative. When heat's pushed to the surroundings, we'd have a negative enthalpy change. Okay, so to make this work, we've actually got to flip the sign of the enthalpy change of the system. Okay, to make predictions of the entropy change of the surroundings, we need to take the enthalpy change of the system, flip the sign, okay, and then that's scaled per temperature. Okay, so this is how we can get the enthalpy change of the surroundings. So you got to be careful on questions when you do your homework at the end of this. I've had lots of students, they try to do a problem like they don't have the information because they're kind of doing the wrong perspective. Maybe they're trying to do the enthalpy change of the system and they're looking for these standard values and they don't have them because the question was asking about the surroundings. Okay. So one last question, I'm going to put the two pieces together. We'll practice both. Okay. What is the entropy change of the universe? Seems hard to believe that we can answer the enthalpy change of the whole universe. We don't even know how big the universe is, but we're going to answer the change in entropy in the whole universe for the production of ammonia at 25 standard conditions. So we're going to use the two pieces that we just learned how to calculate. So I'll get started with the system piece first. Because we're talking about the system, the surroundings, the universe, I'm putting in the subscript for the system. So we'd have to look up, it's not in this slide, we'd go to whatever source or textbook. Our test would need to be given standard absolute values. So we start with products, so we have 2 units times 193 joules per Kelvin. And then in AP we go per mole. Minus, we're done our one product, we've got 2 reactants. And last, we have 3 units of hydrogen. And I get almost minus 200 joules per Kelvin per mole. We got a negative number. Okay, we're saying entropy is decreasing. So it's always worth looking at your equation, seeing if that makes sense. We've got all gases again, so we're not looking at phase changes. We've got 1 and 3, so 4 units of gas becoming 2 units of gas. Does that make any sense with a negative change in entropy? Yeah, we've got less gas phase molecules, so that makes sense. Okay, and you might be able to catch your mistake. It's easy to make a sign change or a sign error in your calculations, and doing that little bit, that check might catch it. Or a whole test question might be just, I give you this equation and ask you to make a prediction. I'll absolutely ask you quiz questions like that. Okay, so we've got that piece. We just have the surroundings piece. Now for the surroundings, we need the enthalpy change and the temperature. So we've got both of those pieces given in our information. So we have everything we need to get the entropy change of the universe. I'm going to kind of jump in and solve everything now. We've already solved for the system. That was minus 199 joules per Kelvin, okay, per mole of reactant. And then I've got to calculate the change in entropy of the surroundings. So that's minus delta H of the system divided by the temperature in Kelvin. So we have our enthalpy change. I'm going to kind of color code things. We've got a minus, and then our enthalpy change is minus 92.6 kilojoules. Now in AP, everything's per mole. So I didn't originally type that in. I kind of left it in the AP version. This is the energy for 132. Okay? But in AP, that's kilojoules per molar amounts. Okay? When you treat those stoichiometric coefficients as moles, that's the energy you get for the equation. Okay? Okay? So that's where this denominator mole came from. It's the AP perspective. Kilojoule. Okay. Then we have to divide that by the temperature in Kelvin. So I converted 25 degrees Celsius to Kelvin. Mostly good. I've calculated the entropy of the system. The surroundings is going to be calculated, but the units aren't going to match. I'm just going to throw in a unit conversion. I got joules here, but I got kilojoules there. So I'm just going to convert them both to joules. So I want to get rid of my kilojoules and get joules. So both terms are joules. So there is 1,000 joules in a kilojoule. And we're almost done. I want to write two pieces so we can compare them first. I'm going to repeat this: 199 joules per Kelvin per mole minus a positive 311 joules per Kelvin . And then we'll put them together in a second. Okay. But what's going on in this reaction is the entropy change of the system, just the chemicals, doesn't want to create a favorable reaction. We're decreasing entropy in the chemicals. But the reaction is so exothermic, there's so much heat being put out, that the disorder created in the surroundings, the 311, is enough entropy increase in the surroundings to overcome the decrease in entropy in the chemicals. So this reaction can happen under standard conditions. Okay? If this had a negative change in entropy, it doesn't matter what you do, it can't run. No catalyst in the world is going to overcome the second law of thermodynamics and make something that's unfavorable happen. So a positive 112 joules per Kelvin per mole is the answer for the change in entropy. Okay. So that sort of wraps up our skills for entropy. So you'll practice some of the math. The next lesson, Gibbs free energy. Okay. So we're working in that Advantage AP Chem 2 workbook. We're done with the 1 workbook and some questions on 186 and 188. And again, just a warning, read carefully about system versus surroundings. That's what leads to most of the error, kind of trying to solve for the wrong parameter.